Assalamualaikum and hi everyone. In this video, we will discuss about second part in this topic, which is about the collision theory. In this subtopic, what you have to know is, first you have to know how to explain the collision theory. The second one, you have to define activation energy. The third one, you have to explain about the transition state theory. And finally, you have to know how to draw energy profile diagram of a reaction. Let's start with collision theory. Collision theory is the ideas of molecules of reactants must collide in order to form products. The second about the collision theory is products are formed only when effective collision occurs between molecules. What is effective collision? The colliding molecules must have a kinetic energy equal to or greater than the activation energy, EA, for the collision to be effective. What is activation energy? It is the minimum energy required to initiate a chemical reaction. Second condition for the collision to be effective collision is the collisions occur at the correct orientation. Let's have a look at this reaction. We have 2Hi gas to produce I2 gas plus H2 gas. In order to form I2 gas and H2 gas, 2Hi molecules must collide in correct orientation so that both molecules can combine to form H2 and I2. So, as this orientation will lead to the formation of H2 and I2, this orientation will produce an effective collision, so the reaction will occur as the product will be formed. Let's look at another case. These two molecules of Hi also collide with each other but in incorrect orientation. At the end, we won't have this product I2 and H2, so this is called as ineffective collision and no reaction will occur. In other words, the correct orientation is when collision of molecules occur at the correct angle that favors the formation of products. Next, let's learn about the transition state theory. It is the theory that explains the activation energy, EA, as the energy required by reactant molecules to form the activated complex at transition state. Activated complex is a temporary species formed by the reactant molecules as a result of the collision before they form the products. The activated complex exists at transition state. Let's have a look at this diagram. This is our transition state. If you can see from this diagram, this is the state when the reactant has the highest or maximum energy before they transform into products. At this transition state, the formation and breaking of bonds occurs at the same time. Now, I want to show you one example. I have two reactants CH3I and OH-. These two reactants will collide to each other to form CH3OH and I-. Before these two reactants transform into products, both of these reactants will combine to form this species, which is called as activated complex. Let's have a closer look. Ci bond of CH3I is breaking while CO bond of CH3OH is forming as activated complex. This activated complex is the species that exists at this state, which is transition state. So that's all about the transition state theory. we go to the last part in the subtopics, which is energy profile diagram. Let's say I have A plus B produce C plus D, and as we know, we have two kinds of reaction, which is exothermic reaction and endothermic reaction. Exothermic reaction is a reaction that release heat or release energy, while endothermic reaction is reaction that absorb heat or absorb energy. In energy profile diagram, we will have these two axes, y-axis as potential energy, x-axis as reaction progress. As exothermic reaction, our energy of product, or I call it as enthalpy of product, is lower compared to enthalpy of reactant. In this energy profile diagram, we also have the activation energy, EA, which is from reactant to the peak of the curve, or at transition state. At transition state, you have to label activated complex as at this state there exists activated complex. Next, what you have to label in the energy profile diagram is you have to label the enthalpy of reaction or change in enthalpy. Change in enthalpy is difference between enthalpy of product and enthalpy of reactant. Since for exothermic reaction, enthalpy of product is lower than enthalpy of reactant, so we will have negative value as exothermic reaction, and in the energy profile diagram, we will label the arrow down to show that energy is released or energy is decreasing. Same goes to endothermic reaction. We will have these two axes, potential energy and reaction progress. For the endothermic reaction, the enthalpy of reactant will be lower than enthalpy of product. Same as the exothermic reaction, activation energy starts from enthalpy of reactant to the peak of the graph. So this is our activation energy of endothermic reaction. We also have to label the activated complex as it exists at this state, which we call as transition state. And lastly, you have to label the enthalpy of reaction, and for the endothermic reaction, we will have positive sign here to show it has positive value, as the enthalpy of product is higher than enthalpy of reactant, and delta H here is when enthalpy product minus enthalpy of reaction, and we will have the positive value. Let's try this example to sketch the energy profile diagram. Given to you the reaction O3 plus O produce to O2. Given to you also the EA forward, enthalpy of reaction or delta H. Then the question asks you to draw a reaction energy diagram and calculate the EA reverse. First thing you have to do is you must draw the axis, which is potential energy as y-axis, reaction progress as x-axis. From the delta H given, we can deduce that this reaction is exothermic, so we have this kind of curve, which is enthalpy of product is lower than enthalpy of reactant. And then don't forget to label the activation energy from reactant to the peak of the graph and also the activated complex. As it already given to you the activation energy, so we label it as EA forward is 19 kilojoule, and the question asks you to calculate the EA reverse. As a reverse reaction, we know that for the reverse reaction, this will be our reactant, and this will be our product. So from the energy profile diagram, as a reverse reaction, this will become our reactant while this will become our product. From the question, the value of delta H reaction is also given. So the value of delta H is the enthalpy of product minus enthalpy of reactant. So as exothermic reaction, so we will use arrow down. This is the difference between product and enthalpy of reactant. So this is our delta H, which is equal to negative 392. Negative here is to show that the enthalpy or the heat is released. As a reverse reaction, this will be our reactant and this will be our product. So EA reverse is from reactant to the peak of the graph, and the value is this 392 plus 19, so we will get 411 kilojoule as our EA reverse. That's all for now. Thank you for watching. I hope you got something from this video. If you have any question, you may leave a comment, consult me or your lecturer immediately. Thank you. Bye.